Well, if you looked online, you'll see that the practice exam for the final is now uploaded there, so you can download that and be taking a look at it on Friday. We'll review a lot of those problems, so think about which ones you want to look at today. And Wednesday, we'll do a little bit of new material still. Try and finish the material for the course. Just by way of review, the weekends always have a way of taking away the momentum. What is the vector line integral? That's what we were doing. The vector line integral of a vector field in the plane, right? So this is in the plane, just I and j, no k element, along a smooth curve C, meaning it has a continuous first derivative. We could write three different ways, just to remind you. We could call it integral along C f dot dr. That was one notation. Another notation was integral f dot t ds. You'll see that frequently. The reason being partly that this one is defined to be this one. When you write this notation, it means this scalar line integral, right? The integral of this scalar function along the curve ds by the definition we gave for that with that square root in it. So then this notation is also used. F1 dx plus F2 dy means the same thing, and you'll see that in there. It's confusing maybe. All you have to do is replace dx with dx dt dt and dy with dy dt dt, and you'll see you get the same integral you do here. In any case, this is the evaluation formula. To evaluate any one of these three integrals, right, I'll write the first notation. You take the integral t going from a to b, where, right, c is parameterized by a vector valued function r of t, t running from a to b, sweeps out the curve. You take f at x of t, y of t along the curve according to this parametric representation, dot dr dt dt, evaluates it. All right, so we proved that from this thing here. And just for your physical information, if you like, what is it we're computing when we compute this? I like it from this definition. It shows you clearly what you're doing. If you take a curve C, swept out by this vector valued function r of t, the terminal point moves along the curve and sweeps it out, right? Here's C. And it's sitting here in a vector field, right? A vector at each point, kind of like gravity or something. Every point there's a member of the vector field. If you take a vector at a point on the curve, and then you're moving along the curve, it has some tangent vector, right? A unit tangent here, t, oops, should look tangent, shouldn't it? Which is r prime over its length. And then what is f dot t, we said? Well, it's length of f, length of t, cosine of the angle between them, but length of t is 1, so it's just length of f cosine of the angle between them. It is, in fact, this side of the triangle. For a unit vector, f dot t is just the projection of f onto t. Right? F dot any unit vector is the projection of f onto the unit vector, is the way it works. And it can be negative if it's opposite direction to f, however. But that's what we're doing, is we're integrating along the curve this component of the vector field. So if f is the velocity of a fluid in the board, right, moving in the plane, then this calculates as the integrand the component of velocity in the direction you're moving. And you're integrating the push or the velocity around the curve, the circulation, the tendency to circulate around this path. Often circulation is applied to closed path. I didn't draw it there, but it still has that computation along a non-closed path. So that's what you're computing. You're calculating if f is a velocity field, the component of velocity integrated along the curve. If f is a force field, then you're taking the component of force along here. It's the work. You're integrating the component of the force pushing you in the direction of the motion. That's called the work. All right, so that's physically what it's doing. I guess I can get rid of this. And now what we finally said was, well, this is applicable to a lot of cases. There's a nicer method that applies if f was conservative. So we'll say, furthermore, if the vector field, and by the way, this can go into more dimensions too, if f of xy is the gradient of some function, then it's called conservative. Or said to be conservative. And again, for a smooth curve and a continuous function, so we'll say under nice conditions, those being the conditions, the integral along C of f dot dr, the work or the circulation, comes out simply to be the potential at the final point of the curve minus the potential at the beginning point of the curve, where Q equals end point of C, P equals the initial point of C. So that can be a lot easier to evaluate than this, right? Sometimes you get a nasty integral here, but if you can just find this function phi, then you just plug in 2 points and subtract, right? And we said that's a generalization of the fundamental theorem of calculus. In one dimension, this is the fundamental theorem of calculus. In 2 dimensions, the problem is that f is not always conservative. In 1 dimension, you only need f to be continuous, and it's automatically a conservative field of in 1 dimension. But in more dimensions, it may or may not be a gradient. And so this only applies to the special case that f is a gradient. Then you can evaluate just by subtracting phi at this endpoint minus phi at this point, and it can be easier than equation 1. Let's call this equation 2. And phi of xy is a potential function for f, is what it's called. Now, I've been saying smooth curves. Actually, you can carry this over to piecewise smooth curves. What a piecewise smooth curve is, I think I mentioned it, but not much. A piecewise smooth curve is a bunch of smooth curves put end to end. So like this, it can have a finite number of points at which it's got a corner, but they're end to end, so they meet. And on each one, it has a continuous derivative. That's what a smooth curve is, has a continuous derivative. And so it only has a finite number of corners is the idea. So this will also apply to that. We won't do it so much for these in this class. I just want to say you can do it. The reason being that then when you do the integral to calculate the potential, have a different function along this piece and this piece and this piece. Kind of like when in Calculus 1, you want to integrate a piecewise defined function, right? You had to apply the fundamental theorem of calculus to this piece, and then add them together. And that was kind of klutzy. Same thing here. You have to do a potential along each segment and separately and add them all together. But you can do that. We'll just do a single smooth curves. So now we did one example last time, and we'll say this extends to higher dimensions. Any finite number of dimensions. Maybe there's some analogy in infinite dimensions. I'm not sure. For instance, f of x, y, z, a vector field with 3 components, f1, I, plus f2 multiplying j, plus f3 multiplying k, along a curve, r of t given with 3 components equals x of ti plus y of tj plus z of tk, t going from A to B, a smooth curve, f with continuous components this applies to, right? If this f is a gradient in 3 dimensions of some potential phi, it's exactly the same result. You just write the same equation. Here it's just it has 3 parts instead of 2. All right, so here's a simple example of that then for today. Suppose I have, let's put it up here. F of x, y, z is cosine z 8y minus x sine z. Suppose we know this is a conservative vector field. Let's find a potential. Remember, all the potentials are equal to within a constant. It's like the fundamental theorem of calculus, just extended. This time, phi will be a function of 3 variables, and its gradient has to be f. Well, remember how you find a potential for a function that's a vector field that's conservative? If it's really conservative, if it's really a gradient of a function phi, then this must be d phi dx, right? The gradient is the vector of partial derivatives. This must be d phi dy. And this one, did I write that down right? Yeah, this one must be d phi dz. If it's really a conservative field. So knowing it's conservative, I'm going to try and find it. I say phi, if this is the partial derivative of phi, must be the partial integral of this. So I integrate cosine z dx, right? This partial derivative with respect to x, I'll do the partial integral with respect to x. Treating y and z both as constants. If y and z are both constants, this is an integral of a constant, so I just get x cosine z. Plus an arbitrary constant, but now y and z were both held constant, so it's an arbitrary function of both y and z. See how it gets more complicated than functions of 2 variables? Now you got 2 variables held constant. That's from the first part here. Now from the second part, since this is the partial of phi with respect to y is 8y, phi must be the partial integral of 8y with respect to y. Now y is the variable, it's not held constant, so the integral of 8y is just 4y squared. Then there's an arbitrary function of x and z, the 2 variables held constant in this partial integration. That's an arbitrary constant. So this is all functions that have partial derivative with respect to y, 8y, right? Is any function of that form. Now, by the third component, d phi dz has to be equal to this. We observe that phi has to be the partial integral of that, minus x sine z with respect to z. Yep. So x is held constant, but integral of minus sine z is cosine z, and so I get x cosine z plus an arbitrary constant. I call this f1. This should be f2, a different function in general. And this one is some function f3 of x and y, the 2 variables held constant. Now, most vector fields are not conservative, and when they're not, you won't be able to make these match. That's the trick. If it's really a gradient, these all match, and if it's not a gradient, they won't. So knowing it's conservative, I know I can make these match. How do I do it? Well, let's see. This looks the same, x cosine z and x cosine z. And that could be x and z are held constant in here. It must be part of this one. And then I have a 4y squared. That could go into here and here because it's treated, those are arbitrary functions of y and z. Evidently, the most general function phi that satisfies all three of those algebraic equations is 4y squared plus x cosine z plus an arbitrary constant. All right, I can add in both of these, all three of these, I mean. Now it satisfies all three of those equations, and that's all of them. And you notice again, there's an arbitrary constant on these. All potentials are equal to within that constant c. Just like when you do an antiderivative of one function, all antiderivatives are equal to within a constant c. So just for convenience, let's choose c equals 0. Because it doesn't matter for the theorem too whether what I pick for c. When I take the one point minus the other and subtract them, the c's will cancel out always, just like they did in calculus 1 for the fundamental theorem of calculus, right? So now, what is the line integral? The vector line integral, f dot dr for this f. Along the curve that goes like this. It starts at 2, 0, and then it goes up here along the arc of the circle and comes down to 0, 0. And I'll draw the arrow to show which way it goes. And maybe this is a semicircle. What is it? By 2, the answer is very easy. I don't have to write a parametric curve. I don't have to take f dot dr dt and all that stuff. What do I just have to do? I say by 2, I can just plug in the endpoints to phi and take the difference. This line integral for the given f is just phi, oops, x, y, z, sorry. This should be 0, 0, 0. I drew it in the wrong space. 0, 2, 0. So it's an x, y, z space. Semicircle in the yz plane. Is just phi at the final point, 0, 0, 0, minus phi at the initial point, 0, 2, 0, where phi is this function here, 4y squared plus x cosine z. So it's 4 times 0 squared plus 0 times cosine 0, plugging in the first point, minus phi at 0, 2, 0 is 4 times 2 squared minus 0 times cosine 0. Gives me negative 8. So there's the line integral. And maybe some of you are seeing something interesting going along already. What if I instead took this squiggle here? What would be the value of that line integral? The same, right? Because I'd say the line integral is phi at the end point minus phi at the beginning point, the same at beginning and end point. So it would just be the same difference. Or I could go spiraling down here like that. I could go any curve I want, any smooth curve I want, and it will give the same result. So let's make that note. Actually, we say that conservative, the line integral of a conservative field is path independent. Any other integral, line integral, a curve from 0, 2, 0 to 0, 0, 0 would have given the same. And it applies to piecewise smooth curves too. It would have given the same result. You just have to evaluate the potential harder. Well, how about this one? Do the same f, but this time I'm going to change the endpoints. Let's do it around the unit circle. X equals cosine t, y equals sine t, and z equals 0. And let's let t run from 0 to 2 pi, so it goes once around. Now what's the result? Yeah, I think I heard it 0. Yeah. You don't even have to do any work. The line integral around a closed path, a closed smooth path of a conservative force is 0, always. Because if you evaluate it, it's just the potential at the endpoint, 0, 0, 0. Not 0, 0, 0. I'm starting at 1, 0, 0. Minus the potential at the endpoint. I end at the same point. Right? They cancel and I get 0. And so there's the second note. Integral f dot dr around a closed path. We put a little circle here to indicate it's a closed path. You don't have to, but it reminds people it's kind of nice. So line integral around a closed path equals 0 for f conservative. In general, it's just by 2. You take the phi at the end point minus phi at the beginning point that are the same, you get 0. So this is a whole lot easier than right, the evaluation formula 1 when f is conservative. Right? Now, that brings something into play. The one drawback to all this, right, was that we had to compute those 3 integrals and see if we could make them equal. If I hadn't been told ahead of time it was conservative, I might do those 3 integrals and say I can't make a match, that the f isn't conservative. It did all that work for nothing. How can I test ahead of time without doing 3 integrals like that, or 2 in the plane, and see if it's conservative so I know whether to do that or not, right? There's a nice theorem, or pair of theorems really, to apply to that. If you want to show f isn't conservative so that doesn't work, you first apply this part. 1, if f in the plane, so I'll put f of x, y, is conservative on an open xy plane region, R containing piecewise smooth. Actually, I don't even need that. Yeah, let's leave that off. Please, an open xy plane region R, then with part has continuous partial derivatives is what I need. First partial derivatives. Then it turns out that df2 dx equals df1 dy. where f, the idea is, as we wrote it before, is some function f1 times I plus some function f2 times j. It gives the field, right? This is an arbitrary vector field in the plane. You give me an x, y, and this gives back a vector, right? So if it fails to satisfy that, you know immediately it's not conservative. What about the other way? How can I make sure it's conservative? Furthermore, if f has continuous first partials, and this holds, the f2 dx equals df1 dy, maybe it's conservative. Do you think it goes the other way? Almost. We say then, let's say on a simply connected open region R, then f is conservative. So we say this almost has a converse. What a converse is in mathematics, if you make a proposition, if P then Q, its converse is the proposition if Q then P. Like if I say to you, if I have $10 and I'm going to go to the movie, right? The converse is if I go to the movie, then I have $10, right? So that's the converse. And that's what we have here. If f is conservative, then this holds. The converse will be if this holds, then f is conservative. It's almost a converse, though. You also need simply connected region on here. Simply connected means it has no holes in the plane region. And it's kind of interesting. If you take, for instance, the unit disk at the origin, here's an open region, doesn't include its boundaries, what open means. This is simply connected because it has no holes. But if I take a single point out of here, like the origin, now it's not simply connected. And there are examples of vector fields that on the disk satisfy this criterion, df2 dx equals df1 dy, on the disk less the origin, but they're not conservative, right? Because the one point is taken out. So this has a converse on simply connected regions only. Don't want to take any hole, no matter how small, out. So let's do an example here. Which are conservative vector fields? So we can apply this theorem, right? Suppose I take f of x, y equals x 2xy I plus y squared j. Is that conservative? On, let's say, the simply connected open region of the whole plane, R2 we call it, right? Whole Euclidean plane. All we have to do is we say this is f1, whatever multiplies I, whatever multiplies j is f2, and we check, is df2 dx equal to df1 dy? Since this is a simply connected open region, this field is conservative if and only if these two are equal. So it's harder in calculus, right? The fundamental theorem of calculus 1. Fundamental theorem of calculus applied to any continuous function you could do that for, and actually to piecewise continuous functions too. But this one only applies if df1 dy equals df2 dx, right? in 2 dimensions. So it gets harder. Most functions are not conservative. If you can't apply this fundamental theorem of line integrals to every field like you could apply to fundamental theorem of calculus to every continuous function. What's the f2 dx? Let's see. Oh, it's 0. What's the f1 dy? Oh, it's 2x. So those are not equal. Therefore, it's not conservative. Well, if x is 0, it's conservative, right? Maybe along x equals 0. No, x equals 0 is not an open region, right? It's the line is a closed subset of the plane because it contains its boundary. So this is actually, there is no open region on which f is conservative. We'll just say it's not conservative because those aren't equal. On the other hand, suppose I take this in the other order. Suppose I take f of xy equals y squared I plus 2xyj. Now is it conservative? Now this is f1 and this is f2. We've reversed them. And we'll say now df2 dx equals 2y. Oh, but that's also equal to df1 dy. So yes, it is conservative. We could apply that theorem. We know we can find a potential function, plug in the endpoints, take the difference to evaluate it. Easier than writing down that equation 1. Okay. Now we want to move it up to 3 dimensions. This is all nice in the plane, but what's the corresponding theorem in 3 dimensions? Here's how we can generalize that one. Similarly, in 3 dimensions, we have f with 3 components on an open region if in 3 space, if f is conservative, the gradient of some function, then this is what you write down, curl of f. Oh, keep writing. Curl of f equals 0. So you can calculate the curl of f, and if it's 0, the 0 vector, then it might be conservative. But if it's not 0, you know immediately it's not. All right, so don't bother trying to integrate. And or let's say, or if f with continuous partials, first partial derivatives, on an open, simply connected region, in 3 space, satisfies this curl equals 0, then it's conservative. There's the almost converse. So in a simply connected open region, here's your test. You just test the curl to see if it's conservative or not, right? Now, some books, I can't remember if your book wrote it this way or not. Some books write it out explicitly like this. You need df2 dx equals df1 dy, which can also be written like this, is 0. And then df3 dy minus df2 dz equals 0, and then df where the df1 dz minus df3 dx equals 0. So some books, I can't remember this one or not now, will write it like this, and this is equivalent to this one because these are the three components of curl. So you can also see it like this, and what you notice now is that the theorem we did for the plane is just a special case of this, right? In the plane, F3 is automatically 0, and 2 of these are automatically satisfied. You just need this one. So these are automatically satisfied in the plane, and this condition in 3 dimensions reduces to this, the first result we put down. Well, that's what you need for conservative in 3 dimensions. You need all 3 of these equations to hold, which means curl equals 0. All right. Sometimes it's easier just to integrate and see than to apply that one. But sometimes it's easier to apply this one. That's a nice result in any case, right? Finally, I'm going to put in one more theorem. Do a guy named George Green. I suggest you look him up on Wikipedia, like just Wikipedia George Green, Google that. He was a guy who only received 1 year of actual formal schooling from 8 to 9 years old. Rest of the time, he was, basically homeschooling himself. He was reading his dad's library and taught himself mathematics. Eventually, I think he went to college or something, but here's a guy who self-taught, became a famous mathematician, but he unfortunately didn't live longer. He's also famous for something called Green's functions, which are useful in higher mathematics. So the theorem due to George Green says this, if f, this one applies only in the plane, has continuous first partials in an open, simply connected region R whose boundary is a simple, meaning not self-intersecting, closed, meaning actually it does intersect by ending where it begins, but otherwise it doesn't intersect. Simple closed is that. Only it ends where it begins, but otherwise doesn't intersect. Piecewise smooth curve traversed counterclockwise. If you take it clockwise, you get minus this result is all. It sounds like one of those machines where it's supposed to make everything harder. What are those called? The what? Yeah, Rube Goldberg. I can't. Goldberg. Yeah, Rube Goldberg. Ever seen that? Those are funny machines that do a simple task. They do a whole lot. Anyway, it almost seems like a Rube Goldberg device here. So let's see, traverse counterclockwise. Then you can take your single line integral f dot dr, any one of those 3 notations, and rewrite it as a double integral over the region enclosed of df2 dx minus df1 dy. And we don't apply this to conservative fields. Why not? Yeah, it works, but it always gives 0 because this is always 0, right? So all it tells you is the result we already knew, that integral around a closed path of a conservative function is 0. Better to write down 0 than to write this and then 0, right? So we're only going to use this for non-conservative fields, but you might think, why do we want to take a single integral and double our trouble, right? Here's why. Generally, we might want to do it. Suppose we have a simple region like a square, and it's traversed counterclockwise, and we want to find the work done around this path, right, in the xy plane. We can break this up into 4 pieces, write parametric curve for all 4 paths, evaluate all 4 line integrals, and add them all together to get the value of the line integral all the way around, applying theorem 2, right? So this breaks up into 4 pieces using formula 1. If it's conservative, then you just write down 0 immediately because it's a closed path. But assuming it's not conservative, we apply Green's theorem and say all we have to do is is one double integral over the enclosed region. And this might be a lot easier because it's just a square goes between constant endpoints, right? So something easy like a square or a circle, if you convert it to polar coordinates so that it runs between constant endpoints, can often be easier to do the double integral once rather than breaking up into a bunch of single integrals by formula 1. So we call this equation 3, and that's Green's theorem. Yeah, and maybe rather than try and do my example when I'm running out of time, I just want to point out one interesting thing about this simply connected region here that we've been mentioning. We said it has no holes in the plane. What about in 3 dimensions? Again, this one only applies to the plane, so we're talking about a plane region with no holes in the boundary that just goes around counterclockwise. Here's 4 piecewise. Here's a piecewise smooth curve with 4 smooth pieces. In 3 dimensions, if we apply suppose we take a ball, right? So take the boundary off. I can draw this dotted or something. This is clearly simply connected, right? Because it has no holes. But the real definition is that any loop inside here can be continuously drawn to a point. So I take a loop inside the sphere, I can continuously draw it to a point. But unlike the plane region, here's a plane region. This is in 3 dimensions, where if I take any point out or any region out whatsoever, a hole, it's not simply connected because any loop cannot be drawn continuously to a point if it goes around this hole, right, without exiting the region. So here, however, if I have a sphere taken out of the middle, it's still simply connected because I can draw the loop around the hole, right, and bring it to a point. So that's still simply connected. Simply connected in 3 dimensions means you don't have a hole drilled clear through. If you drill this hole clear through, now it's not simply connected because now I can put a band around this hole, and I can't draw it to a point without exiting the region. So I just wanted to point out that simply connected in 3 or more dimensions is more awkward. It needs to have a hole drilled clear through to be not simply connected, kind of thing. All right, we'll do Green's theorem next time. That'll be the 3rd way. We'll have formula 1 for general vector line integrals, formula 2 when it's conservative, and formula 3 when it's not conservative, and over a nice plane region, a closed curve over a nice plane region. And I'll put this on here too. You like to draw a circle here to indicate it's a closed curve. I said that up here, but this is a good reminder. All right, thank you for coming in today. We'll finish everything next time and bring questions for me on Friday on the practice problems, please.